doing?
Learning physics.
Physics, you're watching baseball.
Exactly.
Baseball has nothing whatsoever to do with physics. We need to study.
I am studying. You see, the reason we as men watch sports is because we can learn a whole lot about a variety of subjects just from watching.
I think I'm going to need a little proof for that assertion.
All right, I'll give you a nice concrete example using baseball. Come on. Have you played baseball before?
Yeah, a long time ago. I wasn't very good at it. In fact, I think I got a hit about, half the time.
Joanna, the best professional baseball players get a hit about a third of the time.
Really?
Yeah. Speaking of hitting, did you ever hit one that really, really hurt when the ball made contact with the bat?
All the time. I hated it when that happened.
Well, that's physics.
That's physics? I was hoping it wouldn't hurt so much.
Well, it doesn't have to be that way. Take another example. Suppose you're standing at home plate, and the pitcher pitches one to you, and you hit it smooth. I mean, it just takes off, dead straightaway center, flying over the center fielder's head. Now, why do you suppose that is?
I'm way out in left field on this one.
It's because of the sweet spot.
The sweet spot?
Mm-hmm.
That's a great name for a candy store.
The sweet spot is the section of the bat down on the barrel where you're supposed to hit the ball.
Yuck! This isn't sweet at all.
Allow me to explain, all right? It's a figurative expression. It's just a term. It doesn't mean that the bat is actually sweet. It's just baseball lingo for the perfect place on the bat to hit the ball. Somewhere right around in there.
Oh, that makes more sense.
Mm-hmm. You see, when you don't hit the ball on the sweet spot, but you hit it off the end of the bat or on the neck of the bat, it sends more vibrations through the bat, and that's what makes your hands hurt.
Yeah, I guess. You want a lick?
Not right now, thanks. Hold this into the cord and go stand over there. All you have to do is stand there and hold that end in a consistent spot. Now, when I move this end of the cord, it sends transverse waves down the cord. But right now, the waves are not consistent or regular.
You noticed.
Once we get it moving in a regular pattern, you'll notice that there's a spot in the middle that barely moves.
Hey, that's pretty cool.
That spot is what we call a node.
A node, eh? Sounds like you've got a code.
Very funny. See, the node corresponds to the sweet spot on a baseball bat. The vibrations that we see running down the cord are basically what happens in a baseball bat when you hit the ball.
How does that work?
Every time we hit a ball with the bat, it sends vibrations through it. When you hit a ball off the end or on the neck of the bat, the vibrations look like the first ones we had with the cord. They were all over the place. That's why it hurts.
So what happens when we hit the sweet spot on the bat?
We don't feel the vibrations because the sweet spot is a node and the end of the bat where our hands are is another node.
That makes sense.
For sure. Now, have you ever noticed that when you don't hit it off the sweet spot, it doesn't go nearly as far?
No, I don't think I've ever noticed that. I'm usually too busy running towards first base.
Well, you can trust me, it doesn't go nearly as far. And that's because the vibrations waste energy.
So the more the bat vibrates in my hands, the less energy is transferred to the ball, right?
Exactly right. Now for the big question. Why do you suppose aluminum bats are such a big issue in professional baseball?
Because they're too shiny?
Well, that's close, but not exactly. You see, aluminum bats vibrate less, which means there's always more energy transferred to the ball, so the ball is going to go farther. What are you doing?
Well, the way I figure it is, the more bats I have, the better chance I have to hit it.
Whoa, that was some ride.
Yeah, I don't think I'd ever get the hang of that thing.
I still don't think you have. I'm just gonna take these if that's all right.
I didn't think it was that bad.
Yeah, whatever.
So why are we here anyway?
Because golf. is the sport of kings.
Then I'm in the wrong place. I'm not a king, I've never played golf, and what's more, I have no desire to learn how to play golf.
With an attitude like that, it's going to make it that much harder to learn. Come on, you'll be fine.
And if I refuse?
I have this, and you don't. Come on. What if I told you that golf could help you in school?
How? By taking my precious study time? Or I suppose you're going to tell me it's going to help me relax more, so I can study more effectively.
Just take that 5-iron and have a couple whacks at a ball.
How is this going to help me in my schooling?
Just trust me on this one, okay?
See, I can't hit it very far.
Try it again. And this time put some more effort into it. That's a good job for somebody who doesn't really enjoy golf.
Thanks. So how is golf going to help me in school?
Well, we're studying projectile motion right now, right?
Yeah, so?
Well, when you hit a golf ball, it becomes a projectile. You see, when the golf ball leaves the face of the club, it has no means of propelling itself. And that, of course, is the definition of a projectile. Watch. All right, now that one went a long ways, right?
Well, it went farther than mine did anyway.
Okay. Now watch what happens when I hit it with this club. All right, now what was the difference between those two shots?
Well, the first one went farther and the second one went higher.
Exactly, and why do you suppose that is?
I haven't the foggiest.
That's because of the angle on the club face. The driver has a loft on the face of 9 degrees. The loft on the face of the pitching wedge is 50 degrees.
So by hitting the ball with the driver, it flies much farther because the angle is less?
Exactly. It's all in the trajectory.
The trajectory?
Is there an echo in here?
Well, yes, there is. And since I'm here, the trajectory is a path on which a projectile moves through the air. And it's dependent on 2 things, speed and lift.
Speed would be the horizontal plane and lift the vertical plane, right?
Absolutely right. And every trajectory has a certain shape. Now, what shape is that?
A tetrapodahedron?
Close. It's actually a parabola.
Oh, right, a parabola. And what is a parabola again?
Well, every projectile has 2 different types of motion, the vertical and the horizontal.
Vertical is how high it goes, and horizontal is how far it goes.
Precisely.
So what if I use this 5-iron?
Well, ideally, a 5-iron is going to go much farther than a pitching wedge, but won't fly as high, but it'll go much shorter than a driver, but will probably go higher.
Ah.
It's kind of landing in the middle.
Let me try it then.
All right.
Hey, it didn't even go as far as your pitching wedge.
It was probably a defective golf ball.
Thanks. But how could you hit it so far?
Years of practice, dear girl. Years of practice. Hit some more. Come on. It's good for you. Wow, you really are getting the hang of this.
And I'm getting the hang of this, too.
No, wait for me. No, wait, what, come on, wait, slow down, wait. Just you and me now, kid. I'll always take care of you. I mean, I know you're big, you're vulnerable, you're young, but I'll always be here for you.
What are you doing?
Well, I'm pretty nervous about being goalie, so I thought I'd bond with the goal. I'm trying to get the feel of it so I'll be a better goalie.
Well, if you want to be a better goalie, just do some trig.
T-R-I-G, trig is where we want to be. Trig.
I can see that you're questioning me. I'll explain. It's all about angles.
Angles?
Right.
Right angles.
No, not just right angles. The angle from which someone kicks towards the goal greatly affects your ability to defend the goal.
Really? Prove it.
I will, and I'll use trigonometry to prove it. If you're defending the goal from someone kicking straight on, how much undefended space would the kicker have to get the ball into the goal? Let's measure in degrees. In order to use trigonometry, we need to make a triangle. Where would you position yourself if someone was kicking that ball at the goal from the middle?
I'd be standing right here in the middle.
Great. Now the goal is about 24 feet wide. Let's say that the high school goalie can defend about 10 feet of space. Now, don't we need to make a special angle in order to make these calculations?
Right.
You're catching on. Go, 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 Trey! Okay, here's the ball and here's you. We'll have a right angle from the line coming down from the ball to you. Now hopefully you'll be able to cover about 5 feet in either direction. Now we'll put in lines from the ball to where your coverage ends. We're trying to find angles A, B, and Z. Then when we've figured out our angles, we'll double angle C, and then that will tell us how many degrees are vulnerable when someone's shooting into the goal from the middle. Okay, now our formula options are sine equals opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse, and tangent equals opposite over the adjacent. We don't know the measurement of the hypotenuse, but because we know soccer, we know the measurement of the opposite line. That's half the goal, 12 feet. And it's 54 feet for the adjacent line. If we know any two sides of a right triangle, we can figure out anything.
So we're gonna find the tangent of angle A, right?
Right, and that would be 12 divided by 54.
Got something to facilitate calculation? An abacus?
Why don't you try this?
Thanks. Ow! So we got 12 divided by 54 is 0.22.
Great, and the inverse tangent is?
I think I know how to do that. 13 degrees!
Hey, listen up. Now to measure angle B, our adjacent will stay the same, but the opposite will be 5 feet, what you'll be able to defend. So the tangent is?
0.09. And that's 5 degrees.
Now we can subtract angle B from angle A, and that would be about 8 degrees. That's the degrees for scoring a kicker has to get the ball into the goal, giving a total of 16 degrees.
Oh, I don't like that.
Well, now let's measure a kick from the corner of the penalty box, and to see if the undefended space would be more, less, or the same. If I were shooting from this corner, you'd be guarding the goal on this side. Okay, now this angle here will tell us the degrees of the open goal space that you'd be able to cover. And this angle will tell us the degrees that the shooter will have to get past you. Got that?
So we're using the lines of the penalty box for the right angle.
Right. Now in order to solve for the degrees of those two angles, we'll need to calculate these 5 angles. Let's go ahead and label these angles A, B, C, D, E, and F. Here are our opposite and adjacent measurements.
So we're gonna find tangents again, right? Angle A is 55 degrees. Angle B, 50 degrees. C is 45 degrees. So I found angle D by subtracting angle B from angle A. That's 5 degrees.
So what did you do to find the degrees of angles E and F?
For angle E, I subtracted angle C from angle A. That's 55 minus 45, giving me 10 degrees. Then angle E minus angle D is 10 minus 5. So F equals 5 degrees!
We are the best! We are the best! Hey, trick fans, are you there? Put your hands up in the air! If you feel like a trick fan, say it like a trick fan. We are the best! We are the best! So, what'd you come up with?
Well, angle F, which is the angle that I'm going to be guarding, is 5 degrees. And angle D, which is the angle that the guys are trying to kick the ball past me, is also 5 degrees.
Good job!
Thanks, no problem.
So what did you learn using trigonometry that will help you as a goalie?
Okay, I learned that somebody kicking the ball from straight on has 16 degrees to get the ball past me. But somebody kicking from the corner of the penalty box, he only has 5 degrees to get the ball past me.
Let's test our theory.
We're going to start from the corner. Now remember, he's only got 5 degrees to get the ball past the goalie. And he ends up 1 for 5. Well done. Now we're going to move over to the center. Now remember, he's got 16 degrees on either side of the goalie. And he ends up 3 for 5. Wow, that's great. Wow, trig is great for soccer.
Yeah, but who's ever really going to use it?
Yeah, you're right. I guess nobody will use trigonometry for soccer anyway.
I don't think so.
Tennis sure can be a drag.
A drag? I thought you loved to play.
I do, but there's still a lot of drag in the game.
What do you mean by drag?
Here, how would you describe that tennis ball?
Fuzzy?
Exactly. And I'll bet you're wondering, what does that have to do with tennis being a drag? Actually, that has everything to do with tennis being a drag. Drag is simply the opposing force that an object faces as it moves through a fluid. In tennis, the air is the fluid and the object is the tennis ball. As the ball flies through the air, both the object's shape and texture affect drag.
Wow.
Wow's right. There's friction drag and form drag. For friction drag, think first the texture of the ball.
I bet the fuzzier the ball is, the slower it flies.
You're exactly right. And that's friction drag.
Ball, please.
Now, take a racquetball, for instance. Because it's smooth, it has less drag than a fuzzy tennis ball. So there's a reduction in speed due to the uneven surface of the tennis ball. That's friction drag. The less friction drag an object has, the faster it'll be.
Okay, I get friction drag, but what's form drag?
Form drag is the shape of an object that makes a difference in the object's speed and flight. Let's start with the tennis ball, for example. As the tennis ball flies, air pushes against the blunt spherical shape of the ball. This creates high pressure in front of the ball. Then the air separates, going around the ball. Behind the ball, the pressure is less than in front of the ball, and thus we have an area of low pressure. Behind the ball, in the low pressure area, small air currents called eddy currents form. As these eddy currents spin against the ball, they cause the ball to wobble in flight. Golf balls demonstrate a helpful solution to the wobble problem.
Oh, I get it. So that's why they have little dents all over them.
Little indentations, called dimples, cover the surface of the golf ball, creating more eddy currents all the way around the ball. This reduces form drag. Cool.
Okay, obviously this plane here is a little bit bigger than a tennis ball. What about its form drag?
Well, a plane has been aerodynamically designed to reduce drag.
Oh.
Yeah.
Wow. So, tennis really is a drag.
Have you ever thought about how amazing it is to float? What is it that's holding him up?
It's buoyancy. There's a buoyant force holding me up.
I thought it was a canoe. What's buoyant force?
The buoyancy, or I should say the buoyant force acting upon any object, is equal to the weight of the fluid the object displaces.
Wow, son, look at that hippo. Isn't that amazing that a hippo can float?
It's just because there's a buoyant force holding him up, Dad.
Oh.
Let's start with displacement. It's easy.
If you put an object in water, the water will move out of the way so the object can be submerged.
It displaces the water.
So that's why when you drop an object into the water level rises.
It displaces the water out from where the object is.
So the buoyant force is equal to the weight of the fluid that was moved out of the way.
But in case you're wondering what buoyant force is,
It's the water fighting back.
water doesn't like to be pushed around, so it creates a buoyant force. That's the force of the water pushing its way back into its place.
That's why I can float. The buoyant force of the water is pushing me up.
Now I know that he must weigh more than this rock. So if it sinks, he should too. You weigh more than the rock did, so why does the buoyant force hold you up, but the rock sinks?
It likes me. Okay, it's nothing personal. It's just the specific gravity.
Specific gravity?
Specific gravity is related to density. Specific gravity compares the density of an object to the density of water. And we all know that density equals mass over volume. Let's just say that we have two objects with the identical weight, so their mass is equal. But what if their volumes are different?
Then their densities would be different, and that means that the specific gravities would be different too.
Exactly. And if the specific gravity is more than one, that is, if it's heavier than water, the object will sink. But if it's less than one, that's lighter than water, the object will float.
How could you have a specific gravity of less than 1?
The mass of myself and this canoe combined is about 150 kilograms. The volume of this canoe that's submerged in the water with me in it is about 1.25 cubic meters.
So if we divide the mass by the volume, that's 150 divided by 1.25, and we get
120 kilograms per cubic meter.
Then we need to divide that by the density of the water, which is 1,000 kilograms per cubic meter.
And that's 0.12. That's less than 1, so you floated.
You've calculated that my specific gravity is less than 1, so I float. So why is it that the rock won't float?
It's because the specific gravity of the rock is more than 1.
This is fantastic. All these ducks just paddling around without a care. They're not afraid of sinking.
Of course not. They've got a specific gravity of less than 1, so they probably couldn't sink if they wanted to.
Let's review. Buoyant force is the water wanting to push back into place as the object is displacing it. The buoyant force acting on any object is equal to the weight of the fluid the object displaces.
Whether an object will sink or float depends on what the specific gravity of the object is. If the specific gravity is less than 1, the object will float. If it's more than 1, the object will sink. And that's buoyancy.
It's amazing that such a large boat holding so many people can float like that. We had a great trip.
It has to do with the amount of water the boat displaces.
Just watch the boat, son.
Are you sure this will still float with both of us in here?
What's your specific gravity?
That's none of your business.
Well, we'll chance it. Hop in.
Okay.
I've always had a fascination with submarines.
That's not funny.
Shouldn't you be studying for that physics test? And what are you doing with those ridiculous-looking gloves?
Well, if you were paying attention in physics class today, you'd remember that the teacher said that at sea level there are 14.7 pounds pressure pushing down on every square inch of us. These gloves increase the surface area of my hands, and with every extra square inch of surface area, I'm lifting up another 14.7 pounds of air. The way I figure it is that these gloves are going to eliminate the need for actual weights. I'll make a fortune.
Well, I think you should have listened to the rest of the lecture because you're talking about ambient pressure.
So?
Let me explain. And can you listen this time? Ambient pressure is the weight of the air all around us. At sea level, the air presses down with a weight of 14.7 pounds per square inch. That's 14.7 psi, and that's known as 1 atmosphere of pressure. But ambient pressure pushes up as well as down. That means the only weight you're actually holding up is whatever your hands and those gloves weigh.
Well, there goes my patent for these things. You sure do know how to burst a guy's bubble. I was gonna buy a hot air balloon with all the money I made off of those things.
You know something about hot air balloons?
Know about them? Man, I love them.
Well, good. We can study for our physics test together. We'll use the same principles that make hot air balloons float to push our grades up.
Okay. So, what does hot air ballooning have to do with pressure?
Well, you tell me. What makes a hot air balloon rise?
Hot air?
Very good.
Yes!
Why?
I don't know.
Don't worry. That's where the physics comes in. Okay, let's talk about pressure. We already mentioned ambient pressure, which is the pressure all around us. But how is it that we can get into a basket attached to a balloon and then suddenly be able to float?
Well, the balloon is taken out of its bag. Then air is blown into it by a large fan placed at the mouth of the balloon. When it's pretty full, they start heating the air with the burner that's located on the basket. As soon as the air begins to heat, the balloon begins to rise. When it's heated enough, the balloon lifts the basket off the ground along with whatever's in it.
And that's physics.
That's physics?
Yep. Think about what's happening to the air molecules inside the balloon. What does applying heat cause them to do?
Get hot?
Obviously, but what does that do? If molecules aren't heated, they move at relatively normal speeds, and the impacts on each other aren't that significant. When the air molecules are heated, though, they move at much faster speeds and their impacts are much greater.
Okay, I understand that. Heating the air molecules makes them move faster and hit against the walls of the balloon harder. But how does that make the hot air balloon rise?
Well, that's how physics comes into effect. We'll take what you already know, plug it into a formula, and we'll have your answer.
Cool.
First, we know that when the air molecules in the balloon are heated, they push harder on the walls of their container. This expands the volume of the container, but the number of molecules stays the same. We also know that the less dense gases rise. Here's where we need the formula: density is equal to the weight of an object over its volume. So if volume increases, density decreases.
And the balloon rises, and rises, and rises.
Now that you're back down to Earth, maybe we can continue studying for our physics test.
I don't know that I can handle all this pressure. Hey, you ready to start working on that project?
Oh, what project?
The physics project.
Oh, that project. Yeah, I'm ready. In fact, I've already started working on it.
No way!
Yeah, this Bernoulli guy is totally cool. He discovered a principle that is very essential in knowing how airplanes fly.
I know. I've been researching him too. But Bernoulli's principle doesn't just apply to airplanes.
Are you sure you've been researching the right guy?
Yeah, Daniel Bernoulli, born in 1700, he discovered the principle that the faster a gas or liquid moves, the lighter its pressure.
That's right. And this is how it's applied. The top of an airplane wing is curved. So when the wind hits it and divides to go around both sides, the airflow going over the top moves faster than the air on the bottom. Because the airflow going over the top of the wing is moving faster than the air going underneath the wing, the air pressure on top is less than the air pressure on the bottom.
Don't forget the second half of Bernoulli's principle. Areas of higher pressure push towards areas of lower pressure.
I hadn't forgotten. The slower moving air underneath the wing has a higher pressure, so it pushes upward where the pressure is lower. And that moves the plane upward and forward. And that's Bernoulli's principle. Has everything to do with making airplanes fly.
And that's also why race cars drive so fast.
What? I'm telling you, Bernoulli only deals with planes.
Listen, I guess I'm just gonna have to prove it to you. Have you ever seen a spoiler on the back of a car?
A spoiler?
Yeah, a spoiler. You know that fin-looking thing? Okay. Anyway, why do you suppose a driver needs that?
I have no earthly idea, but I suppose you're going to tell me that has something to do with Bernoulli's principle.
Exactly. It has everything to do with Bernoulli's principle. You see, the curve on a race car spoiler is opposite that of an airplane's wing. Therefore, the airflow on the bottom moves faster than on top, so the pressure on the top is greater.
And the air pushes the car down more, so the tires get better traction with the ground.
Exactly. It's Bernoulli's principle.
Okay, so Bernoulli's principle applies to planes and other things with wing-like parts. Now, can we get started with this report?
No. You still haven't got it figured out. Bernoulli's principle applies to more than planes and things with wing-like parts.
Sorry
about that. Oh, we'll be quieter. I'm sorry.
Okay.
Okay, now take a sailboat, for example.
Okay, I see it. Now, are you going to tell me this has something to do with Bernoulli's principle, too?
Yes, based on Bernoulli's principle, the curve of a boat's sail is extremely important to its movement. When the wind hits the sail, it splits to go around both sides. In order to meet at the back of the sail at the same time, the airflow going around the curve of the sail moves faster than the air moving around the other side. So if the wind on this side of the sail has a higher pressure, then that pressure is pushing towards this area. The higher pressure pushing towards the lower pressure moves the boat forward.
Wow, I guess Bernoulli's principle really does apply to more things than just planes.
You can say that again.
Wow, I guess Bernoulli's principle
Hush.
does.
And we've barely scratched the surface. Bernoulli's principle applies to airplanes, race cars, sailboats, hydrofoils, birds, tennis balls, hurricanes, tornadoes.
Whoa, Bernoulli's principle is like everywhere. It's all around us.
Well, I wouldn't quite go that far, but at least now you understand that Bernoulli's principle applies to more than just planes. Now, come on, I've got a physics project to do. Ow, what was that for?
You're so loud.
I'm not. I'm not.
Do you have a pen?
Yeah.
I don't really know a whole lot about volleyball.
That's all right. I'm just getting ready for tryouts next week, and I need someone to practice with. Maybe I can teach you a few things. Woo!
All right, but I warned you. What are you laughing for?
I don't think you're going to be needing those.
Well, Mom said I should wear knee pads.
Okay, let's start with serves. Whew, I guess I do need more practice. I only got 3 out of 5 serves. That's just 60%.
Well, what do you want to know a boring statistic like that for? Statistics and probability is really boring stuff. I'm all about the action in sports.
But we draw important conclusions about sporting events based on stats. Football, baseball, volleyball, soccer, and even golf use stats. You wouldn't call that boring, would you? Let's bring this down to practical level.
Okay.
Suppose that we had a volleyball player that had a percentage of 92 when serving.
Okay.
That means, statistically speaking, out of every 100 serves, 92 of them are going to be put into play.
Did you just make that number up?
Well, yes, but in reality, we use numbers and raw data, what's actually happening in the game. Now, how do we find out if a volleyball player has a 92% average?
Well, we take the average of her height and her weight, and then we divide by 6 and add the square root of 14.
You know better than that. We use stats. We'll gather 2 numbers, the total number of serves and the total number of serves put into play. And we'll use those 2 numbers to find the percentage.
So because you served 3 out of 5 in, you have a serving percentage of 60%?
Right. Now, how did you come up with that percentage?
I divided the number of serves you got in play, 3, by the total number of serves, 5. That equals 0.6 or 60%.
Exactly, but when you're dealing with stats, you want to get as much raw data as you can get because it makes the percentage more precise. You see, I was able to serve 60% of my 5 serves, but I might also miss the next 5.
So we're just gonna sit around and watch you serve all day.
Well, there are actually 2 different kinds of stats. There's descriptive and inferential.
I'm guessing that descriptive statistics describe things and inferential statistics probably infer things.
Big words. But what do they mean?
Well, since you're the one that knows all about this, I'm going to defer to you.
Descriptive stats summarize and describe what happens, and inferential stats help us draw conclusions based on smaller data.
What can we do with that?
Well, 60% is a descriptive stat. It describes exactly what is happening. I served 3 of my 5 serves in. From an inferential point of view, I could infer that the next time I serve 5 serves, I will hit 3 of them in.
Try it.
Okay. Well, I did a little better that time. I got 4 out of 5. That's 80%. So if I put my 2 totals together, I made 7 out of 10, which is 70%. So just by getting 1 more in on the second set of serves, my percentage went up 10%. That's why statisticians like to have as much raw data as possible. Now let's try inferential statistics.
I don't know, that sounds pretty difficult to me.
It's really not that hard. Here's an example. Suppose my team had a record of 15-3, and we were going to be playing a team who had a record of 4-16. Who do you suppose would win?
I'm guessing the team that has 15 wins.
Why?
Well, because they have more wins, they're probably better than the other team.
Well, that's inferential stats. They describe the probability of something happening.
Okay, here's another example for you.
Okay.
Suppose we had a volleyball player that's averaging 10 kills per match, and we get to the last game of the match and he's only got 4 kills. That means he's going to get 6 kills in that last game, right?
Well, not necessarily. Just because a player averages a certain number doesn't mean he's automatically going to get that precise number.
It doesn't?
No, not at all. It's just his average. It'd be like if we said a volleyball player averaged 12.4 kills a game.
Oh, I think I'm starting to get it. But there's something I still don't understand. How can you end up with 0.4 of a kill?
You can't. That's just the average. It doesn't have to work out in whole numbers.
Oh. I think my brain hurts.
Any more questions?
Yeah. So, based on statistics, we can infer that our spiker is going to get about 12 kills the next game, right?
That's exactly right.
Good. That's cool. I'm starting to get the hang of this. Now, come on. Let's go practice our spiking.
You've got a long ways to go. You need to work on those serves first.
What are you doing?
I'm working on improving my average speed.
Average speed? I say, why would you want to do a thing like that?
I want to cover the greatest amount of distance in the shortest amount of time. That's average speed.
You don't have to accelerate like that! Right! 2 can run this race! Okay, let's say you go 100 meters. A go-kart? Whatever. So it takes 10 seconds to go 100 meters. To find the average speed, I simply divide the distance by the time. That's 100 divided by 10, and that gives me...
10 meters per second.
That's my average speed.
But what about your instantaneous speed?
If I had a speedometer on this machine, I could measure the instantaneous speed easily.
Instantaneous speed is an object's speed at any given instance. Let's say I wanted to find the average speed of the go-kart at the instant it crossed the 50-meter mark. We're going to measure the time at 5 meters before the mark and 5 meters after the mark. Then we'll find the difference in those two times. We know that the change in distance will be 10 meters, so we'll divide 10 meters by the time, and that'll give us a good approximation of the instantaneous speed at the 50-meter mark. My runner is going to record the time of the go-kart as it crosses over the 2 points. Then we're going to find the average speed between the 2 points. Ready?
Ready.
Ready? Ready! I say!
The time at the first point was 6.25. Then at the second point, it was 7.1 seconds.
So if we subtract those two times from each other, that gives us 0.85 seconds. And we know that the distance was 10 meters. 10 meters divided by 0.85 seconds is 11.8 meters per second. So that's the approximate instantaneous speed at 50 meters.
Now let's figure out the acceleration.
Acceleration! Acceleration is the change in an object's velocity over a certain period of time. Why don't we calculate acceleration from where the go-kart started at 0 seconds and 0 meters to 50 meters? Because we already know the instantaneous velocity at that point.
Your starting velocity was 0, and your velocity at 50 meters was 11.8 seconds. So that would be your change in velocity. Your starting time was 0, and your time when passing the 50-meter mark was 6.7 seconds.
How did you know that?
I timed it when you weren't looking. Anyway, that's the amount of time it took for your velocity to change.
So if I divide 11.8 by 6.7 seconds, that gives me 1.8 meters per second squared. So now we know average speed equals distance divided by time. And for a short interval, we could assume this to be the instantaneous speed.
And now we know acceleration equals the change in velocity divided by time.
And the acceleration is measured in meters per second squared. Hi, Joe. You know, it seems ironic that we're studying equilibrium and force in physics right now. And here I am at a skating rink to get a few lessons. Equilibrium and ice skates are an oxymoron for me. My expert teacher asks if I would like to take a few laps around the ice to get warmed up, while I inform her that just standing up is quite an accomplishment for me. She, on the other hand, goes ice skating nearly every week.
Our Sunday school was going ice skating in about 2 weeks, so I was hoping to teach him something about skating. But after seeing his wretched condition, I realistically told him I wasn't sure how much I'd be able to help him. I also really needed to spend a lot of time studying for our next physics test, the one about equilibrium and force. No problem, he told me. He made a bargain that he'd help me with equilibrium in physics, while I would help him with equilibrium on ice skates. I have to admit, I didn't see it at first, how equilibrium and gravity have anything to do with ice skating. But you were right, it sure does.
Yep.
What are you doing?
I'm demonstrating another principle of physics right now.
The pull of gravity?
Close, but not quite. This is actually one of the 3 types of equilibrium.
Oh, it's neutral equilibrium.
Exactly.
And I pointed out that standing, I was demonstrating stable equilibrium. All the forces acting on my body were in balance because my center of gravity was centered right over my feet. So I don't lose my balance if I'm standing straight up. Now, what is an example of unstable equilibrium? Ouch! You were an unstable system.
My center of gravity wasn't centered above my feet, and the forces were overbalancing and working against the equilibrium. In attempting to get back into balance, they merely made the situation worse. I think I'm just gonna stay in neutral equilibrium for a while.
When all the forces are in balance, that's called balanced equilibrium.
Yes, but at every moment we have forces acting against us. Things like ice skates, rails, ice, and even my own feet.
Well, you're right about the forces acting against us. Gravity pushes down on us, the ground pushes back. And as long as they're equal, we're in a state of equilibrium. Now, everything has a specific center of gravity, and when this center of gravity is changed, the equilibrium must be changed.
So when I'm on ice skates and I can't yet stand up straight on them, my center of gravity keeps shifting and I'm in a state of instability. Thus, I fall.
You were right. Physics has a lot to do with ice skating. Poor guy. At least now you know why you keep on falling.
Oh, thanks.
Well, I tried to help you, didn't I?
Yes, my brilliant teacher had a unique idea, as you can see. Fortunately, my job was just to stand in the same spot. Thus, we demonstrated another physics principle. I started leaning back so she wouldn't pull me over.
In other words, he automatically compensated for the force working against his equilibrium by leaning backwards.
As she spun around me, centripetal force pulled her toward the center of the circle, and I leaned backwards to equalize that force that pulled her toward me. Oh, the room is still spinning around me.
Well, what I want to know is how torque fits into all this.
What would we need to do in order to make us balanced on this board?
Well, if we made your end shorter and my end longer, then we'd be balanced.
Exactly. Well, let's look at it this way. We have two forces. One is 200 newtons and the other is 100 newtons. How can we balance the board?
Add 100 newtons to the other side.
Let's try something else. We know that torque is force times radius. We know the downward force on each side.
Oh, I see. So in order to balance it, we need to have the same torque on either side.
Yep. Let's say that the radius of the 200 newton object is 2 meters. How long would the radius need to be for the object that weighs 100 newtons?
I'll do the math. The torque of the 200 newton object is 200 times 2, and that's 400. Now for the 100 newton object, the force is 100 newtons and the torque needs to equal 400. So the equation will be 400 equals 100 times the radius. So we divide each side by 100, and that leaves the radius as 4.
You've really got a pretty good grip on this torque and equilibrium thing. I, on the other hand, I think I need a little more practice.
Hurry up there.
I'm coming.
Yeah, you was always a little bit slow.
Who you be cheering for today?
Well, I reckon I'll cheer for the boy again today. He seems to play pretty good.
You're wrong. You're wrong.
No.
She can dunk all on his head.
Oh, but I seen this boy play. He got an absolutely sick spin move, and he can finger roll like the Iceman.
But he's got no jumper. She can stick the J anywhere on this court.
Yeah, but this boy's got the D to shut her down. She won't be able to shoot that jumper with him guarding her.
Oh, shush.
We each have won 2 games.
And today we find out who the real champion is, and it's gonna be me. Sorry.
I'm gonna go get a drink. You go get the ball.
Okay, yeah, fine, whatever.
All right, I'm ready to go.
All right, you got the ball first.
Okay. What are you trying to do, Andy? Demonstrate a lack of air pressure or the law of gravity? Or are you just stalling because you know you're going to lose the game?
I think he's stolen.
Oh, no. He's a smart one, this boy, is he?
Wrong, but thank you for playing, and we have some lovely parting gifts for our second and third place contestants today. So why does a basketball bounce?
Because it has air in it.
Well, this ball has air in it too, but it didn't bounce nearly as high as one of the other balls. Why is that?
Because it needs more air?
It needs compressed air. That's what makes an aired-up basketball bounce much higher than a flat one.
compressed air has less space between the molecules. When those molecules are compressed even more than they already are, like when a ball is dropped to the ground, they make every effort to push the container back to its original shape. So when the basketball hits the floor, it's an elastic collision.
So what's an elastic collision?
An elastic collision is one in which all the energy of the particles is conserved. That's why a basketball bounces.
Dropping a bowling ball onto concrete is an example of a more inelastic collision, one where part of the particle's energy is changed into a different form, like heat. It's not full of air, so there's no reaction by compressed air, so it won't change its shape and won't bounce nearly as much. The particle's energy will be mostly released as heat.
I just can't do it.
A basketball is full of compressed air, which means when it hits the ground, it can change its shape.
The air molecules inside will be even more compressed and will rebound to their original shape, the very thing that helps conserve the kinetic energy.
Speaking of energy, my mom made some of those awesome chocolate chip cookies. I think you probably ought to have a few before I completely thrash you in this game.
I think it's you who's gonna need a last meal before I cream you in the next game.
Whatever.
But your mom does have some awesome cookies. Come on, let's go.
These is really good cookies, Myrtle.
Yep.
How much they cost?
Why, Cyril, I've been making you these cookies for 35 years. They're your favorite.
Really?
Yeah.
I don't remember that. What kind are they?
But here's another question for you. How do we know that the basketball is always going to bounce to a consistent height?
Easy. Every basketball has a consistent pressure. See, right here next to the hole where you air it up, it has a number.
79 psi.
PSI means pounds per square inch. If aired properly, the basketball will have 7 to 9 pounds of air pressure pushing against every square inch of the inside of the basketball cover.
Makes sense.
However, I don't know why there are different PSIs for footballs and volleyballs and soccer balls and everything else.
Different sports have balls with different PSIs because the higher the air pressure inside, the more the ball is going to bounce.
Because of the higher pressure inside the ball pushing back out.
So we know that the ball is going to bounce to a consistent height because of the coefficient of restitution.
And that's the thing that measures how high the ball will bounce back after being dropped from a certain height.
Yep.
The formula for finding the coefficient is the square root of the height of the bounce divided by the height from which the ball was dropped.
The rules say that a regulation basketball, when dropped from a height of 6 feet, has to bounce back up to somewhere between 49 and 52 inches.
To find the coefficient of restitution on a basketball, let's suppose that the basketball bounces to a consistent height of 52 inches.
We divide 52 by 72, which is the number of inches, and find the square root of that, giving us a coefficient of 0.85.
So what we found is that the basketball itself doesn't matter that much. It's the air pressure inside the ball that makes it bounce. This is a breeze.
Just like I'm going to breeze past you on my way to the hoop.
Told you that boy would win.
Yeah, but she took him over into overtime.
It doesn't matter. Did they say when the rematch was gonna be?
Yeah, tomorrow morning. We coming?
Yeah, wouldn't miss it.
Shall we start our game now?
Oh, I reckon we might. Yeah.
All right. I'm always up for creaming you.
Oh, you ain't never creamed me in your life. I'll cream you like that can of corn we had last night.
I'll cream you like cream of mushroom, cream of chicken,
Cream of wheat.
celery.
You ain't cream of wheat. Come on, hurry up, Myrtle.